Okay, welcome everybody to the next session. I guess the speaker doesn't need much introduction. You've probably already seen him last year or the year before or the year before that. For those who haven't, this is Dan Kaminsky. As you can see on the slide, he's the Director of Penetration Testing at IOActive. And well, he's the guy who gave us SSH over DNS, and he will certainly go to hell for tunneling DNS over SSH over DNS, but maybe he'll tell you later. Okay, enjoy the talk.
All right. If you can get any lights killed on that, that'd be awesome.
Okay.
What's up, guys? So I'm out here. Actually, wait, do I actually need this hand mic? I think I can just use this thing. Rock on. All right. I've got way too much material to go over, so let's start. Yay, Swiss Hotel, screw you, Delta Hotel. You dropped a TV on my laptop. Who am I? Some guy. What are we here to do? Break stuff. I do like the pretty pictures. I just have a particularly peculiar definition of pretty. But before we go into the pretty pictures, how many people here thought we couldn't possibly have any more hideous TCP/IP stunts? I mean, come on. It's 2006. Leave the poor thing alone. No. No. We're going to have some fun here. So, see, the great thing about the future is just when the network works, people are like, damn it, the network's working. Let's break it some more. Our net is fast. Why are you working on making it slower? So you've got all these oligopolies who are like, wow, we can't make money with fast net. Let's make money with slower nets. So they're doing all this weird stuff with network neutrality. Thus, people start coming to me, hey, Dan, can you bust them? I'm like, maybe. So what's the closest tool we have to find a network that's screwing with packets on a per-host basis? Well, we've got, who here knows, has ever used Firewalk? Rock. Who here has ever used Traceroute? Much better. Firewalk is Traceroute, but instead of using just random packets, you use some sort of packet that you'd actually want to pass through a firewall. And it's a very simple idea. You send your HTTP request 1 hop, 2 hop, 3 hops, 4 hops. Oh wait, it died on hop 4. But if I send SSH, it dies on hop 7. Maybe there's a firewall between hop 4 and hop 5 that's blocking my HTTP packets. So that's what's going on with that. That's how Firewalk works. Now, Firewalk tells you what gets through. It does not tell you who. You can't Firewalk to find out if some other network has special abilities. Well, this suddenly devolves to a very nice question, which is we've always wanted to know what firewall rules someone has, not just with what they'll pass, but for who they'll pass them for. Was there anything we could possibly do? Well, TCP actually is able to do speed measurement on networks in a very interesting way. You've got all these nodes that are communicating, figuring out how fast they're going to send packets, and they don't actually talk to each other. No. You know how the routers tell them to slow down? They drop their stuff on the floor. It's a very small back channel, but it works. And it works kind of well. And it tells us about other people, other hosts, other IPs on the network. Could we possibly combine this with Firewalk? Well, of course we can. What causes packets to drop? Sending too many packets. What are we going to do? We're going to send too many packets. Rock. We set up 2 channels. One is our primary channel. Whatever we get back from, we're not spoofing our source IP. We're actually getting feedback on this primary channel. But there's a second channel. Another stream of packets, extra traffic on the network causes drops, not necessarily coming from us, could be coming from anybody. But how do we know if it gets all the way through? Because it causes our primary channel to start dropping. Think about this. Think about how this merges with Firewalk. Normally, you don't know which packets, you don't know what other packets are on the network. You don't know what's causing your packets to drop. But in this case, you do know because you're sending the packets. You know exactly what they are. You know exactly what they're composed of. And if by some chance some firewall was blocking those packets before it could get onto that router, where it would overload the link and cause packets to drop, well, if it's being firewalled in advance, well, guess what? Now you know. Oh, wait, if I send packets from here, it causes drops. If I send packets from there, no drops. The packets must be getting dropped for some other reason. So you can actually use this to very effectively find hosts that are doing filtering, not just on what, but on who. So I'm calling it scorch marking. Why do I call it scorch marking? Well, routers are burning packets, so I figure maybe a couple that are getting through have some scorch marks. Basic model, you download a file from a site, it sends it to you as fast as possible by TCP, and you just start sending more packets. But not from you, from other people. And if your TCP stream slows down, you know, oh wait, there's no block, it's just normal. But let's say it doesn't. Let's say, you're sending as fast as you can, and then you spoof a bunch of traffic from, I don't know, their internal video provider, and those packets get through great. You're like, oh, those packets are preferred. They're allowed to pass anyway. They don't cause drops to happen. So here are some problems. Having to depend on a client is lame. Wouldn't it be nice if you could just scan the internet for routes that were all messed up? Well, let's think about this for a second. When a client is downloading a file from you, what's it actually doing? What is the fundamental service that this client is providing? Well, this client is just acknowledging your traffic. It's saying, yeah, I got that, and TCP does the rest. Well, by any chance, are there other ways that clients could acknowledge traffic from us? Well, yeah. TCP servers acknowledge traffic. You send them a SYN, they give you a SYNAC. DNS servers acknowledge traffic. Routers. Routers will send you ICMP time exceeded messages. When you are running traceroute, you're saying, I'm sending this packet out 3 hops, and you get an error message. You didn't just get an error message, you got an acknowledgement. It saw what you had to say, and it's saying, oh yeah, I saw that. I'm not routing it any farther, but I saw it. So guess what? You can use all your TCP bandwidth estimation stuff, but you can just bounce it right off of ICMP time exceeded messages. Now, theoretically, these messages are rate limited. Realistically, no. You can pass as many as you want, and you'll get as many errors back as you like. It's actually kind of nice. So you can scan for violations of network neutrality. You can find networks that are blocking and passing IP ranges, but it's not exactly efficient. You really have to have a slow link that you're overloading. Now, before, back in the day, you'd never have a firewall before the slow link. You'd never have a firewall in your ISP path that's preventing you from getting fast networking. Nowadays, we have new situations and thus new tools. There's a bigger problem, though. In order for this method to work, you kind of sort of have to DOS some links. DOSing isn't good. DOSing isn't scalable or, ethical, legal, good stuff. So your potential solution would be to find capped acknowledgers. Now, the rumor is that there are actually boxes that are limiting how many time exceeded messages they'll send you. Without having to overload the CPU, overload the link, it's just they'll only send this many errors per second. Great. Thank you. Now you don't need to overload the link, you just need to fill the buffer. And how is this going to work? Your primary channel is also going to be using time exceeded messages. So your primary channel is requesting time exceeded, your secondary channel is either not getting packets through or it's taking slots from your global list of how many time exceeded messages per second you're willing to send. If you can actually find boxes, say, I don't know, like Linux Linksys boxes that everyone has on their cable modems, if you could possibly find boxes like that, maybe you'd be able to get some progress without, knocking boxes off the net. So that'd be cool. Now, if you have code on the client, there might be some cool things you could do using Windows Media Player. Believe it or not, there's actually more than just DRM in there. It will receive video streams over this great protocol called RTP. And it will receive it unicast, UDP, and it will send back quality metrics. How many packets got through, what the jitter was, what the latency was. And you know where it'll send it? Somewhere else. Thank you. So you just spoof a bunch of traffic from YouTube, spoof a bunch of traffic from MySpace, and say, oh, and can you give me the feedback on how many of those packets got through? Yeah, and that should actually work. But we didn't actually come here to talk about TCP/IP hackery. It's just sort of my thing. Let's talk about SSH, which, crap, that's also sort of my thing. So you gotta love SSHing into hosts, right? You go in, the authenticity of this host cannot be established. Do you recognize 09, A9, B1, 99, 84? what? Am I supposed to do something? Yes, says SSH, you're supposed to recognize it. And if you don't, you're insecure and a bad human being. Yeah, this totally doesn't work. But it's one of those dirty little secrets, right? Well, let's fix it if we can. By the way, hex sucks. I know we all like looking through hex dumps, but seriously, hex sucks. The human brain, not built to deal with that. It's sure as hell not built to deal with that. There are exceptions. I know them by name. I worship them. They scare me. We got to find a better mapping. So, cryptonamonics is a field created specifically because the name sounds awesome. There are 3 classes of memory that cryptographers actually want you as the human to have. Rejection, I've never seen that before. Recognition, it's you and totally not you. And recollection. So he had like a nose this big and like hair, you know, bringing back from the top of your head. Passwords are recollection. Now, all SSH actually needs from you is rejection. What the hell is that? You know, I say what the hell is that, but it's the real thing. Well, the hex domain doesn't work. What else is available? Well, let's restate the problem. Humans do not operate on hexadecimal symbols effectively. Are there any other symbol sets that we can use that the human brain is actually compatible with? And the answer is, well, let's take a look around. There have been some other attempts. One group went ahead and used artwork, computer-generated artwork with some fixed parameters. Another group used human faces that were automatically generated. In both cases, what they did is you would look around and see a bunch. You'd say, okay, her, and then him, and then her. And it actually kind of worked. The brain does have some hardware acceleration for faces. The problem is, believe it or not, some people lose it, actually. It's a form of brain damage. Believe it or not, it does work, but it doesn't work that great because you have very little entropy you can actually represent. If you're given 5 choices of 1 out of 9, you have like a 2 to the 16 chance of, you know, just guessing the right one. Well, that's not enough for what SSH needs. SSH needs 2 to the 160, which is quite a bit more. So we need better than this. Well, here's another domain. I'm calling it the mnemic domain. It's basically names. You know, humans, we actually do have memory. You know, we don't remember arbitrary bits, we don't remember hex, but we do remember stories. You know, Homer's epics are enormous, and for most of human history, those were oral stories that were passed down from father to son, mother to daughter, and so on. Well, stories do change over time. You know, basic things stay the same, but there is drift. But you know what actually doesn't drift too much? We still call the guy Homer. So names are actually fairly stable in stories. We seem to have hardware acceleration for them. So could we map the 160 bits that SSH needs us to accept or reject, could we map them to names? Well, let's take 512 male names, 9 bits, 1,024 female names, 10 bits, more variability in female names, quite a bit actually. 8,192 last names. That's 13 bits of information per last name. 9 plus 10 plus 13 is 32. With 5 couples, you can actually represent a 160-bit key. It ends up looking like this. Julio. Now, you might say, but how would I ever recognize these names? I actually went for 6 months logging into every host that I use using these names. Believe it or not, you actually start recognizing them. It's certainly not hex. Now, it is critical. Every time you log in, you see these names. You know why you forget names, by the way? Because someone says, hi, I'm Bob, blah, 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 blah. Like, what? Huh? So it's really all about being constantly exposed. Then the brain's able to actually finally pick it up. And remember, you don't need to repeat it back or anything. You just need to, like, see it and be like, oh, yeah, him. Like, wait, that's not Jane. That's, well, someone else, but certainly not Jane.